Thank you, everyone. Hi, my name is Yingqi. Welcome to this talk. And today I'm going to talk about our work, PICCOLO exposing complex backdoors in NLP transformer models. And this is a joint research work between Purdue University and Rutgers University. Backdoor attacks has shown a severe threat to the NLP transformer models. And here, let me use a very simple sentiment classification model to illustrate what is backdoor attacks on NLP models. First, given backdoor NLP models, when facing with clean samples, it gives the correct model predictions. And when the input contains a trigger, the backdoor models misbehave and give the wrong predictions or give the predictions that the attacker desires. Here, in this case, the trigger is a hash sign at the beginning of the sentence. Besides the character triggers I have just shown, the triggers could also be like word triggers or phrase triggers, and they can be injected at any place, any location in the sentence. And the trigger could also be more complex. For example, the sentence structure triggers. The clean sentence reads as, "There is no pleasure in watching a child suffer." And the sentence with the trigger reads as, "When you see a child suffer, there is no pleasure." Note that the sentence structure is swapped. And the when you subclause is injected at the beginning of the sentence. This when you subclause is actually sentence structure triggers. So to combat backdoors in machine learning, in computer vision, the trigger inversion is highly effective in detecting backdoors in computer vision. So let me first introduce what is trigger inversion in computer vision. It assumes access to a model and a set of clean inputs. Then it stamps a random trigger on the clean image, and they feed this stamped image directly into the input layer of the model. And then optimize the trigger on the input space such that the model's output label is flipped to a target class. Note that in this case, a both image is flipped to the target class car. And because the model is differentiable from the input to the output, we can simply do a gradient descent on the input and you invert the trigger that flips the labels. If a trigger can flip most of the clean inputs, the trigger inversion consider a model Trojan. Note that in computer vision, the model is differentiable from the input to the output. So we follow the classic attack model of trigger inversion in computer vision. We see an NLP classification model is chosen if the model does not have a non-trivial accuracy degradation on clean inputs, and the model misclassifies input with the trigger. And for defender setting, we assume the defender is given the model and a few clean sentences, and she needs to determine if the model is chosen or not. And note that defender has no access to the inputs with triggers. Before diving into our method, let me first briefly introduce the typical structure of NLP transformers. So given a text input, given a sentence, the NLP transformers will first parse into a list of token IDs. Note that complex words will parse into multiple IDs. For example, here the word judgments is parsed into 2 IDs. And then each token ID is used to look up for an embedding vector with the size of 768. This E equal table ID is an indexing operation, and it is not differentiable. Then the embedding vectors are fed into the transformer to give the final output. Note that in traditional computer vision models, the model is differentiable from input to output. However, with the unique structure of NLP transformers, poses new challenges in trigger inversion in NLP. Our first challenge is that the input space is discrete and NLP models are not differentiable to the input. This lies in the table lookup operation that maps the token ID to the embedding vectors. Note that this is an indexing operation and it is not differentiable. And in trigger inversion in CV, we can just do the gradient backpropagation from the output to the input. However, the gradient propagation in NLP cannot go through the table lookup to the token level. So to solve the first challenge, we propose a differentiable model transformation. It essentially just transforms this non-differentiable table lookup into a differentiable matrix multiplication that is equivalent. So given a list of token IDs, we first transform them into a list of one-hot vectors, and we call it token vectors. So for token ID n, the nth element of the one-hot vector is 1, and all other elements are 0. For example, for token ID, for the first token ID, 1119, the 1119th element is 1, and all other elements are 0. Then, instead of do a table lookup, we can simply get the word embeddings by multiplying the one-hot token vectors with the lookup table. And this is equivalent to the table indexing. I will use a simple example to illustrate this. Let's say we have a small lookup table with just 4 entries, and our token ID is 1. Then the indexing of our operation, we will just simply select the second vector, 0.3, 0.2, 0.7, something. And the corresponding one-hot vector is 0.01000, where the second element is 1 and all other elements are 0. Then do a matrix multiplication on the lookup table. We can simply also get the same vector, 0.2, 0.3, 0.75. And this is equivalent. So the multiplying the one-hot token vector and the lookup table is equivalent to the indexing table. And if we think about it, as long as the sum of the token vector is 1, the token vector can also be viewed as a probability distribution of the token IDs. So we can optimize on this token vector to invert the trigger. So let's go back to our model transformation. After we have the one-hot token vectors, we can get the word embeddings by multiplying the token vectors with the lookup table. And we can feed the word embeddings to the transformer to follow the whole pipeline. And this operation is differentiable, and the gradients can backpropagate from the model output to the two token vectors. And similarly to trigger inversion in CV, we can just inject a trigger vector in the token vector level to do the trigger inversion. However, then we met our second challenge. Token level optimization cannot reverse engineer complex words with multiple tokens. For example, here our example trigger word is word immensity. And in BERT, it's split into 3 tokens, IM, MEN, SITY. And assume we know the number of tokens we need, and we use exactly 3 trigger token vectors in trigger inversion. And the optimization shows the result is 3 tokens, IM, VN, and DOTY, and it misses the real trigger. And these 3 inverted trigger can only flip around like 70% of clean samples, and it is not good, high enough for trigger inversion to determine this model is chosen. So to invert complex trigger word, token level inversion can easily get stuck in some invalid token combinations and misses the real trigger. So to solve the second challenge, we propose word level inversion. Here I just show the token level inversion on the left for comparison. So given a text input, given a sentence, we first pass them into a list of word IDs. Note that our word vocabulary contains many complex words, so they don't need to be split into multiple tokens. For example, here, the word judgments only correspond to 1 ID. Then similarly, we can do a one-hot vectorization and get the word vectors. And similarly, we can get the token vectors by multiplying the word vectors with the word to token matrix. And we can get the word embeddings by multiplying the word token vectors with the lookup table. The whole process is differentiable. And we can just invert the trigger at the word level. And here, notice that because we use a large word vocabulary, we only need 1 trigger vector to invert complex words such as immensity, and this reduces the search space and helps the trigger inversion. So in this slide, I will show how to do the word level inversion. First, we inject a vector in the word vectors. We call it trigger probability vector, where each element stands for the probability of that word, their corresponding words being the trigger. And since we have made the whole pipeline differentiable, we can just backpropagate the gradients from the model output to the word vectors and optimize this trigger probability vector in a way that it flips the model prediction on the clean samples. We also bound this trigger probability vector trigger probability vector to be between 0 and 1 by tangent edge. And we also normalize this trigger probability vector to the sum of 1 in every 30 epochs. So after the optimization, words with high values in the trigger probability vector we call it trigger word candidates, and we test them for the attack success rate. So here is an overview of our method. Given a model M and a set of clean inputs, we first transform this model M into a differentiable equivalent model M prime, and with the clean inputs, we do a word level trigger inversion and get a list of trigger word candidates. And then the trigger word candidates is fed into a word discriminativity analysis and trigger validation to determine if the model is chosen or not. In the first two steps actually corresponds to the two challenges I have talked about. And in the word discriminativity analysis, for complex words, it is possible that we only invert a partial trigger word and it doesn't have high SR. So we test the word discriminativity of the trigger word candidates to determine if a model is chosen. And for trigger validation, we simply test the attack success rate of the trigger word candidates and determine if the model is chosen. Due to the time limit, I will elide the details of the last two parts. So in evaluation, we evaluate PICCOLO on 7 data sets: Amazon Review, IMDb, Yelp SST2 for sentiment classification, CONLL 2003, BN Corps, and On2 nodes for name entity recognition. And we also evaluate our method on 7 NLP architectures: BERT, DistillBERT, MobileBERT, JoBERTA, GPT-2, and simple LSTM and GRU. And we also evaluate our method against 3,839 NLP models from the TrojanEye computation and the existing works. And we also evaluate PICCOLO against 17 different attack types, including the latest dynamic attacks, the sentence structure trigger. Before going into the evaluation details, I want to first briefly introduce what is IARPA's TrojanEye computation. It is a multi-year computation for backdoor scanning. It is still going on right now. And it is open to public, so anyone can participate. It has 9 rounds so far, targeting for both computer vision and NLP. And at each round, TrojanEye has like thousands of models, half clean and half chosen, and they ask the performers to submit their predictors that predicts which model is contains backdoor. And performers need to submit their scanners to the TrojanEye remote server, which evaluates the evaluation against the test and holdout sets. The test and holdout sets, we cannot access the test and holdout sets, and they can have a more robust evaluation. So the round target is around like 0.34 cross entropy loss, which is often correspond to around like 90% accuracy. So the current TrojanEye leaderboard is can be accessed at this website. And here I show a screenshot of the TrojanEye leaderboard. As you can see, they have your evaluation server, and you can submit your container to the evaluation server to get your method tested. And here I show the screenshot of the current rounds TrojanEye leaderboard. So in effectiveness, our PICCOLO achieves over 0.9 detection accuracy for all the evaluated attacks. And in TrojanEye computation, PICCOLO is the only solution that beats the round goal in all 3 NLP classification rounds, and PICCOLO achieves the top on 2 out of 3 NLP rounds in TrojanEye computation. So here I show a table of the TrojanEye leaderboard with our method PICCOLO and other teams' best submission. TrojanEye computation released 2 metrics to measure the scanner's performance: CE loss and ROC AOC. So a lower CE loss and a higher ROC AOC indicates better performance. And as you can see on round 6 and round 7, our method PICCOLO is the best among all the participants. This is related work to our method. Due to the time limit, I will skip this. And also, we share our method and our TrojanEye submissions on different rounds in our online code repo. To summarize, we developed a novel backdoor scanning technique, PICCOLO. PICCOLO is based on a novel word-level encoding and word discriminativity analysis. And based on the TroJI computation results and evaluation, PICCOLO achieves the state-of-art results for complex models and a wide range of backdoor attacks. Thank you. That's all. I'm happy to take any questions.
So we have time for questions, and as usual, please feel free to don't be shy, walk to the mic, state your name and affiliation. I can probably break the ice, no? You have a question.
Hi, Giorgio Severi, Northeastern University. Great talk and great work. I have a curiosity to ask you. Did you notice differences in effectiveness of your system on different sizes of the models you analyze, like bigger models, models trained with bigger data sets, smaller data sets?
Yeah, that's a great question. So on, let me go back here. So on the 7 different NLP architectures, we do a kind of like a statistical check, and we find that actually on Roberta we are a little bit worse than on Roberta and JPT2 we are a little bit worse than BERT and DC BERT and mobile BERT. But overall the architecture does not matter that much. In terms of like different attack types, we handle the freeze trigger the worst because we are inversion technique, and usually it's very hard to invert a whole freeze. But the details can be found in our paper. Thank you.
I have a question.
Yes.
So you mentioned that to make the whole model then differentiable, you don't rely on token inversion anymore, but then you use word inversion.
Yes.
Because you have to do the one-hot encoding and then multiply that matrix and to make it work.
Yeah.
You said that in the example, for instance, you need to have the word in your vocabulary, right?
Yeah.
So how big is the?
Yeah, that's a great question. So so several things. First, so in the system that's submitted in the paper, at that time we have like 7,000 as the word vocabulary. And in adaptive text, we have increased the vocabulary from 7,000 to 30,000. And because the TroJI competition is still going on, and in the latest round 9, we increased our word vocabulary to over 100, over 100,000 based on the word frequency in the Wikipedia data set.
Right, and how do you see this improving? Like, have you tried to compare the performance as the vocabulary size increases? Like, there is a point where you have a saturation point that adding more words doesn't look like
that's a great question. We have done adaptive attack on like if the word is outside the word vocabulary, and we find that as long as we can increase the size of vocabulary, we can still have a good performance. And in terms of the competition feeling, we feel that the previous rounds, the solution that works on the like round 7 and round 8, it's not that effective on round 9. That's why we go from like 20,000 to like over 100,000 in to achieve good performance in competition.
Okay.
Yeah. Thank you.
Wonderful. Thank you.
Thank you.
So if there are no other any other questions, so we can thank the speaker. Thank you very much.